Hello everyone and welcome to another video. As you undoubtedly know because you clicked on the link to this video, what I want to talk about today is velocity and acceleration in rotating reference frames. This is a really important topic and I'm very excited. The first reason is, if you think about it, we live on a giant rotating reference frame, but in a lot of our dynamic models and simulations, we fail to take this rotation into account. We're going to see that this has a potential to introduce some non-trivial errors in many reasonable scenarios. The second reason I'm so excited about this is because we've been building up to this discussion over the course of the last 3 videos. Hopefully you've watched these previous videos on expressing vectors in different frames using rotation matrices. In this video, we started building up some of the framework and infrastructure, including notation on how to deal with vectors that are expressed in different frames. If you haven't had a chance to see that, you can get to that video by just clicking on the card right up here. After we did that, the second thing we looked at was using some of those vector concepts to go ahead and derive Rodrigues' rotation formula, also known as Goldstein's rotation of a vector formula. And we saw that what that allowed us to do is talk about how vectors are able to be rotated about some arbitrary axis of rotation. Again, if you want to see that video, again, here's another card, click on that and it'll take you to that video. Thirdly, we took both of those concepts and finally put them together here to start looking at vector derivatives, or how do these vectors change with respect to an observer in different frames, right? So that was also known as the more popular name of maybe the equation of Coriolis, right? Again, click on the card if you'd like to see that video. So what's so fun about this discussion now is that we finally get to use those 3 videos that we talked about as a building block and foundation for the current discussion on velocity and acceleration in rotating frames. So with that being said, I really would strongly urge you to watch those previous videos if you haven't done so already. Just go ahead, pause this video, click and save it to your watch later list or something like that, and watch these 3 videos first. The links to all 3 of these previous prerequisite videos are all in the description below. And when you're done with that, why don't you come on back here and we'll go ahead and set the stage for why you would actually care about talking about velocity and acceleration in rotating reference frames.
To set the stage for this discussion, let's consider a scenario that everyone's familiar with. Consider an Imperial Star Destroyer cruising through space. Suppose you're a gunner fresh out of the Imperial Training Academy and you've been placed on this Star Destroyer under the command of one Captain Nida. Things are going great until one day everyone gets the following memo from the Emperor.
Commander Kelly, the time has come. Execute Order
67. Due to a galaxy-wide energy crisis, all energy weapons on board Imperial vessels are to be immediately replaced with 14th century cast iron cannons. Those failing to comply will answer directly to Lord Vader. Well, that's a little bit scary of a message, so naturally Captain Nida complies and installs these projectile weapons and pulls the turbo lasers offline. Everything is business as usual for a few days, hunting for rebels, enslaving Wookiees, and looking for droids. But one day, you happen to glance through the portside viewport and see a rebel X-Wing. Captain Nida decides to destroy this rebel scum and tells you to lock on at once and point the cannon directly at the X-Wing. However, in your haste, you neglect to notice that the Star Destroyer is traveling at velocity Vs, and the target is traveling at velocity Vt, which is less than Vs. Let's examine what's going to happen in this scenario. Let's call the Star Destroyer the Observer. The first thing that happens is that the Observer fires the cannonball. The cannonball then leaves with the same horizontal component of velocity as the Star Destroyer, Vt, while the X-Wing travels at the slower velocity Vs. The end effect is that the cannonball passes to the right of the X-Wing. Now, remember that the observer on the Star Destroyer is just looking at the inky blackness of space and the X-Wing. From their point of view, it seems like some mysterious force appears to push the cannonball to the right. And it's somewhat appropriate that we're talking about Star Wars here, because it almost seems like there were some Jedi on that X-Wing, but that can't be true, can it? The Emperor just issued Order 67, which replaced all the lasers with cannons, and in his previous directive, Order 66, that resulted in all the Jedi being wiped out, right? There aren't any Jedi that somehow escaped and maybe are now hiding out in disguise on some backwater planet, are there? Anyway, as an informed bystander, we know that this effect is due to the relative motion of the two reference frames. Of course, this is of little solace to Captain Nita. He's going to have to explain this little mishap to Darth Vader.
Captain, Lord Vader demands an update on the pursuit. Get a shuttle ready. I shall assume full responsibility
For not understanding relative motion and its potential applications to non-inertial reference frames.
and apologize to Lord Vader. Meanwhile, continue to scan the area. Yes, Captain.
Apology accepted, Captain Nita.
So in the interest of ensuring that this doesn't happen to you or anyone you love, we should finish the rest of this discussion and learn about non-inertial reference frames. A somewhat similar scenario actually occurs every day. Not a long time ago in a galaxy far, far away, but right here on planet Earth. If you think about this, since the Earth is rotating, people or objects that are closer to the equator are actually moving faster than people closer to the poles. In 1651, Italian scientist Giovanni Battista Riccioli and his assistant Francesco Maria Grimaldi examined the exact scenario of firing an artillery shell northward and arguing that it should be deflected to the right due to this effect. 23 years later, in 1674, Claude François Millet Deschaux described in his Cursus Seu Mundus Mathematicus how the rotation of Earth should cause a deflection in the trajectories of both falling bodies and projectiles aimed towards one of the planet's poles. Interestingly, Riccioli and Deschaux used this description as an argument against Copernicus's heliocentric model. In other words, they argued that if Earth was indeed rotating, then these effects should be present. So failure to detect these effects must mean that Earth is sitting here static and not rotating. It turns out that these effects did indeed take place, but the magnitude of these effects are small for most of the applications such as the ones they studied. It wasn't until almost 100 years later, in 1749, when Euler applied this knowledge to develop a formal modern expression for acceleration in rotating reference frames. Let's see if we can follow in his footsteps and derive an expression for acceleration in rotating reference frames.
All right, so the goal now is to try to develop expressions for velocity and acceleration in rotating reference frames. So the first thing we should maybe do is draw a diagram of the scenario to discuss position here, right? Because position is obviously the first step to getting velocity. And just to refresh your memory here, so the picture I want to draw now is, if you remember our discussion we had earlier with our F-14 model here, and we said we're going to attach a body frame to this thing, like something like this, and we're looking at how this thing rotated, and we're talking about how the pilot's perspective of a point on, say, like the wingtip changed as this point was moving and as the aircraft was rolling around. So again, we discussed all of this previously in the prior video here, talking about vector derivatives and the equation of Coriolis here. So I want to draw the picture here of how this body frame sits relative to an inertial reference frame here. So let's draw that diagram, or maybe more accurately, redraw the diagram of what we talked about in that previous video. So in the previous video, right, if you remember, we had a frame of reference down here. I'll just try to draw it sort of like this, maybe. We called this our reference frame, FR here, right? And it has an X, Y, Z. I don't think we actually need to label these, and we just want to say that it's some three-dimensional reference frame out there. And then we had another reference frame. Maybe we'll do it in a different color, say blue here. And this was the body frame that was attached to the aircraft here, right? So again, this thing had an X, Y, and a Z here, right? And this was the body frame, F body, right? And now what we did is we said that, okay, there's some different points that we can start talking about. We can start talking about what's the position vector of the body frame with respect to the reference frame here, right? So we said that, okay, there's going to be this red arrow, or a red vector, which represents the position vector of the body frame with respect to the reference frame here, right? And then we said we might have some point of interest out here, like the wingtip of the aircraft. Maybe we're going to call this point P out here. And we can talk about how is that point P related to the body frame. So let's draw another vector here, maybe in green here. This is going to be the position vector of P with respect to B here. So I think that's a good start on some of the objects that we need here. So here's the very abstract diagram. Now what we can start asking is, let's go ahead and describe the position of point P with respect to an observer on the reference frame. So position is actually really easy. So position, we can just write this using a simple vector sum, right? So if I want to know what is the position of point P with respect to the reference here, well, we see that this is really simple. It's just a vector sum here. So I just need to get this red vector added to the green vector. So this is RB with respect to R added to RP with respect to B. There we go. So this here is the position of point P with respect to an observer in the inertial reference frame here. Let's go ahead and label this as an equation. In my notes, I have this just as equation 3. So I apparently defined 2 other equations previously that I didn't write on the board, but that's fine. I just want to give this a unique label, okay? So now, can we get an expression for velocity? Right? What is that? Question mark here, right? So what we can probably do is, let's think about taking a derivative of the position vector to get the velocity vector, right? That seems completely reasonable. Let's do this over here where we got a little bit more room, all right? So what we're really talking about right now is to get the velocity vector here, we want to go ahead and take the derivative. So again, let's write this down here. So I have, here's the position vector, R, P with respect to R, right? This is going to be R, B with respect to R plus R, P with respect to B, right? And now all I want to do is I want to take the derivative of this, ddt, right, of this thing. So I'm going to go ahead and ddt both sides. Right? But now, this is interesting because this is where we saw earlier that our notation was a little bit inconsistent. We saw that the derivative of a vector depends on whose perspective you're asking, right? We want to see this changes from whose perspective. So we got to add that notation here. Again, what we really care about is I want to know how is this green vector changing if I'm sitting on the inertial reference frame here, right? So I really want to see how is this thing changing with respect to frame R here, right? So let's go ahead and do that for all of these here, right? Okay, so again, the left-hand side, our notation for this, right, we said that, okay, this can just be simply written as R dot P with respect to R, and then we're going to use the left superscript to denote which derivative this dot actually refers to, right? So this is something like this, right? That's the left-hand side. And now this equals both of these two combined here. So we got to go ahead and look at these carefully here. So let's look at this first term here, right? This is not too bad, right? Because we see that what this is really asking about is how is the frame, the body frame, moving with respect to the reference frame in a translational fashion here, right? So there's no rotation here. This is just saying how fast are the origins of these two coordinate frames moving away from one or the other, right? So we could just go ahead and write this first term here. This is, we can write as R dot B with respect to R from the R frame here, right? There's no rotation involved here, right? That red vector is just going to move. It's not rotating. Now, this is where it gets interesting. This is the exact scenario we looked at in the previous video here, right, where we were talking about vector derivatives. This is asking how does that wingtip vector change, right? But how does it change from the perspective of the observer on the reference frame? So we see that we need to take into account how is the body frame rotating here in this term. So this second term is a little bit more complicated. Maybe let's put this in parentheses here. So we see that this term becomes what's here in parentheses. And again, we see that this is really just, we need to apply Coriolis here, right? So we're going to apply the Coriolis equation that we developed in the previous expression, right? So we saw that, all right, the derivative of this thing, so again, it's the vector itself, p with respect to b, the derivative with respect to the body frame, right? Plus, how is the body frame, omega b with respect to r, moving crossed with the vector itself, rp with respect to b, like that, right? So this is now Coriolis, right? Okay, so great. So I think we're pretty good here. There's a couple of things that we may want to do and clean up here. So this is an accurate description, but I think it would be more helpful if we maybe rename a few of these terms here. So let's just go ahead and do a couple of things here. So let's go ahead and define this term. Maybe I'll write this here in red here. So let's make this term here. We'll go ahead and call this the velocity of b with respect to r. Again, a vector, right? Okay, that's what this term, that's effectively what it's talking about, right? It's the velocity of that point P as the observer on the ground sees it. So again, this is what we're after, okay? Let's think about some of these other terms here. So this thing right here, again, we talked about, this is just a translational velocity of how the two frames are moving with respect to each other. So again, instead of having to write all these dots and subscripts and superscripts, let's just go ahead and call this is the, where did I actually have the notation here? Yeah, here, wait a second. Yeah, this is velocity of b with respect to r, right? Okay, all right, and then in here, let's take a look at a couple of these here, right? So for the sake of notation here, this thing right here, right, if you look at this, this is how is that point moving from the perspective of the observer on the body frame here, right? So this is really, it's the velocity of point P with respect to the body frame. So this superscript is actually almost a little bit superfluous. I think everyone would agree that, you know what, if I call this VP with respect to B, doesn't that sort of give you the exact same information here? So I think it's clear here that this is the velocity of point P with respect to the body frame. So yeah, that seems to make sense. So great, let's call this, and then everything else I think is fine. Okay, great. So with that, we can go ahead and come up with a slightly cleaner expression for velocity here. So we end up with, and actually, you know what? Let's fill it in over here. This is what we're looking for here, right? So the expression for velocity that I'd like to write down is we can basically say that, okay, the velocity of P with respect to R, right? That's what we're looking for here. This is going to be the velocity, the translational velocity of the two frames away from one another or towards one another here, right? Plus the velocity of P with respect to B, plus, wait a second, BR, P. Yeah, perfect. Okay, this plus omega B with respect to R crossed with RP with respect to B. Great. Okay, let me just triple check to make sure I got all that correct. Omega B R. Yeah. Okay, perfect. All right. So here's our expression for velocity of point P with respect to an observer on the inertial or the reference frame here, right? Okay, great. So then probably the logical next step here is I got the position vector, I got a velocity vector, I need an acceleration vector here, right? So let's talk about acceleration. And again, we're going to play the exact same game. What is this equal to here? Right? So let's come back over here. Let's go ahead and erase all of this. And we're going to play the exact same trick, although it's going to be a little bit more complicated now, as I'm sure you can kind of see right now. Okay, so acceleration is just the derivative of the velocity vector here. So all I need to do here is take the velocity vector and differentiate it. So let's go ahead and write down our velocity vector here, right? So this is V P with respect to R is equal to V P with respect to B plus, oh, sorry, whoops, I skipped one. This is the first term is B with respect to R, right? B with respect to R plus V, whoops, I should have vectors on all of these. V P with respect to B plus omega B with respect to R crossed with RP with respect to B. Okay. All right, there we go. So take a time derivative, ddt of this whole thing. And again, we are going to take the time derivative of this with respect to the inertial frame here, right? So let's just do that here. ddt with respect to r of this term, ddt with respect to r of this term, plus ddt, crud, I ran out of room. I should have planned this a little better. Let me see if I can scoot this over so it's not so blocky. R of omega b with respect to r crossed r p with respect to b. Okay, so what we should do here is let's tackle this one term at a time here, right? So again, the left-hand side, this is what we're looking for here, right? So over here, this is v dot p with respect to r from the reference perspective here, right? It's now equal to these three terms. Let's call this first one maybe like a term 1, maybe a t1, plus this thing right here could be term 2, right? And then this whole derivative of this cross product, let's make this entire thing something we're going to call t3 here, right? So all I want to do now is let's examine term 1, 2, and 3 one at a time here and expand them, okay? So let's start here. So term 1. So t1, just to refresh your memory, I need to go ahead and figure out what is ddt with respect to r of v b with respect to r. Okay? So once again, actually, if you look at this here, since vb with respect to r is actually, it's what? It's the translational velocity of frame b relative from frame r. We're now looking at how does that change as we look at it from frame r. So if we take the derivative once more with respect to frame r, we simply obtain the acceleration of frame b relative to frame r here, right? So what we could say is this is just, let's call it, how about a b with respect to r again, right? So this is the translational acceleration of the two frames away from each other that don't involve any rotation here, right? So great, we're done with term 1. That wasn't so horrible. Let's go ahead and look at term 2 here. So t2 here, right? T2, yeah, t2, not the Arnold Schwarzenegger kind. So this is now ddt with respect to r of vp with respect to b. Okay? So, again, let's think about this. This is the point, like on the wingtip of the aircraft. How does it change with respect to the body frame, but as seen from the non-rotating inertial frame? So again, this is just the equation of Coriolis one more time here, right? So this is not an issue. Just go ahead and apply Coriolis one more time. So what we end up with here is, we can just write this as, okay, this is the vector derivative dot, right, as seen from the body frame, plus how is the body frame rotating with respect to the reference frame, crossed with the vector itself, right? The vector itself is just VPB, right? Yep, V dot B. Yeah, great. Okay, so there we go. That's term 1 and 2, not too shabby. Now term 3 is where we're going to get a little bit messy here. Tell you what, in the interest of trying to conserve sport, I guarantee that this will not be enough space. Can you commit these two to memory here, right? Or hopefully you guys have written these two expressions down here. You know what? Actually, here's what we can do. Let's put them down here in our giant acceleration expression down here that we're going to start building up here. So the acceleration expression here that I'm looking for is, okay, the total acceleration here on the side here is, I'm looking for this, right? That's the total inertial acceleration from the reference frame, right? This is going to be, all right, term 1. What do we say? This is a b with respect to r, right? Plus term 2, which we just worked out, right? And did I actually make any simplifications? No, I don't think I did. Okay, let's write this down. V dot p with respect to b from the b frame plus omega b with respect to r crossed VPB. Okay? All right, so that's term 1 and 2 here. And now let's erase the board here so we have enough room to work out term 3. Okay, so term 3. Right, and this one's a doozy. Okay, so term 3 here. We're looking for ddt with respect to r of omega b with respect to r crossed r p with respect to b. Right? That's what we're gonna look for here. Okay, so let's go ahead and do the product rule here for this cross product. So I want to take the time derivative of this, so it's going to be product rule, right? Time derivative of this thing, time crossed with this, plus this crossed with this time derivative, right? So in other words, this is crud. Am I gonna have enough space? Yeah, I hope so here. So ddt with respect to r of omega b with respect to r crossed with r p with respect to b, right? Plus omega b with respect to r crossed with ddt with respect to r of r p b. Great. Okay, I think we got that here. All right. Now I guess we got to pick apart each one of these 1, 2, 3, 4 terms here, right? Okay, so let's take a look at this here, right? What is this thing? This is the angular velocity vector, right? That's omega b with respect to r. That's the angular velocity vector of how b is rotating with respect to r. Now I want to see, how does that vector change from the perspective of the reference frame? Now, if you remember our discussion on the angular velocity vector, I believe we said that it really doesn't matter which frame you're looking at it from. I think there's just a -1 in here, depending on whose perspective you're asking, which flips these indices. But really, if you think about this long enough, this is really, it's not the angular velocity vector. This is now the angular acceleration vector, right? So this entire thing here, maybe let me do this in another color because this is going to get a little bit messy. Let's call this entire thing here. Where did I have the notation here? Yeah, this is this is alpha b with respect to r, right? So this is the angular acceleration, and the reason we got this here, right, is we said that this is really omega b with respect to r dot with from the r perspective, right? And we said this was the exact same from our properties of the angular velocity vector, that this was the same as taking the derivative with respect to the body frame here, right? So all we're going to say is, let's just call that thing alpha b with respect to r, right? So again, you can think about this as the angular acceleration of the two frames as they rotate with respect to one another here, right? And again, maybe you don't have to worry too much about writing down what each one of these terms mean. Once we get a giant ugly expression for acceleration, we'll list out explicitly what each topic or what each term is. Okay, great. So that's what we've got here. So we're making progress. Okay, this I don't think we need to do anything with, right? Okay, don't need to do anything with. This guy, what is this? If you look at this, isn't this what we did earlier? Look at this. This is the position vector, right, of p with respect to b. So this is the rotating bit. This is the thing on the body frame as seen from the reference frame. So again, this should be screaming Coriolis equation again to you. So this thing right here, again, let's maybe use red here to show that, okay, I can go ahead and we already worked that out once here. So this is actually going to be, yeah, earlier we worked out during our velocity expression here, right? I believe we said that ddt with respect to r of rp with respect to b, right? This thing right here, this is going to be, actually we said it's the velocity of p with respect to b plus omega b with respect to r crossed rp with respect to b. So actually, maybe I didn't need this side because it's just rewriting twice. But anyway, this black term is the same as this red expression here, right? That we worked out one step earlier when we were dealing with the velocity here, right? In fact, yeah, you see it right here, right? It was this component of it, right? Okay, great. So that's term 3 here, and actually, I think we're probably in a good spot that we can maybe go ahead and substitute that in. So let's just rewrite this on the and tack it on at the end of our giant acceleration expression here. Okay, so we got this. All right, so this is now right. Okay, so plus, what do we got now? Plus alpha b with respect to r crossed with r p with respect to b, all right, plus omega b with respect to r wait a second, where? Oh, no, yeah. The alpha, yeah, right. Crossed with, in parentheses now, substitute that other expression for the velocities, Vp with respect to b plus omega b with respect to r crossed r p with respect to b. Yikes. Ugly expression, but it's correct here. So now, the last thing we want to maybe do now is, let me erase some of this so we can get some more space here, is simplify this thing a little bit. Because if you look at this, if you go ahead and distribute this cross product through, and you're going to notice that some of these things are going to show up multiple times here, right? So if you look here, for example, there's this omega b with respect to r crossed b. There's this term, right? So you can see it actually shows up again here, right? When you distribute this cross product through this portion, it's going to look like this. So there should be something like a 2 times omega b with respect to r crossed Vp with respect to b. All I'm saying here is, if you do a little bit of algebraic boring manipulation on this, you can rewrite this entire thing here. Let's go ahead and write it actually up here. That might be useful, because this is sort of the end product here of the discussion of where we're trying to get to. Okay, so you do all of this stuff here, right? So, yeah, maybe we should, okay, yeah, sorry, I should maybe make one more change in notation here, right? This is what we're looking for, right? This is the acceleration of point P with respect to R from the inertial reference frame here, right? So this whole thing, I'm going to go ahead and call this thing acceleration of P with respect to R, right? That's what we're looking for here, right? So the entire this left-hand side this is the normal acceleration you would see in a normal inertial frame. So if nothing were rotating, this is your normal acceleration here that you would expect here, right? So what we can write here is, all right, that's what I'm gunning for. I want a P with respect to R is equal to something. And now the fact that the body frame is rotating is going to screw us over and make our lives a lot more complicated here, but also a lot more interesting and a lot more rich here. So I'm just going to say, do boring algebraic manipulation on this, and you can massage that whole thing to look like this. A B with respect to R plus A P with respect to B plus 2 times omega b with respect to r crossed v p with respect to b plus alpha b with respect to r crossed r p with respect to b plus, this last term, I guess I ran out of room, plus omega b with respect to r crossed with the quantity omega b with respect to r crossed rp with respect to b. Great, and we really should box this up, because this is our acceleration in a rotating reference frame equation that we're looking for here. Now let's talk about what each one of these terms are here, right? So in this case, right, this first term, AP with respect to R, right? This is the same thing as we said earlier, the time rate of change of the velocity of P with respect to R from the reference frame here, right? This is sometimes referred to as your true acceleration. Okay? Because again, you can actually kind of see if nothing were rotating here, a bunch of these terms drop out here. But this is true acceleration here, right? This is the normal acceleration we've been dealing with your whole life when you're writing dynamics equations or things like that. This is plain old normal acceleration. Now, let's talk about this term, A, B with respect to R here, right? So this is the translational acceleration of FB relative to FR, right? So in other words, is this frame B, is it accelerating away from frame R? How's it translating when it does that here, right? That's what this vector describes, okay? And then we have this term here, right? A P with respect to B. Whoops, respect to B, right? So we said also this was the same notation as velocity of P with respect to B, its time derivative with respect to the body frame here. Right? I think that's the substitution we made earlier, right? So this is actually the interesting term. So this is sometimes referred to as like the relative acceleration. So in other words, it's the acceleration that you would see if you're sitting on frame B here. So this is relative acceleration as seen from FB. So in other words, what the pilot of that aircraft would say, how is this point P accelerating? That's his answer. This is what he would give, right? Okay, and then we have omega B with respect to R. This was our typical angular velocity vector. So it's the angular velocity of FB relative to FR, right? Okay, what other expressions have we got in there? Oh, we had this this term here, right? VP with respect to B, right? We said that this was our shorthand notation, so we didn't have to keep writing this, right? So this notation, though, is a little bit more helpful because it allows us to see that, all right, what this term is really describing here, it's the relative velocity as seen from FB here, right? So this is relative velocity of point P as seen from F body, right? Okay, second to last here, I think we need this alpha term here. So alpha B with respect to R, right? So this was the angular acceleration of FB relative to FR. Okay, and the last term here, gosh, we're sorry, this is getting kind of busy. I'll tell you what, let's erase this bottom line here because we don't need it. We already got the better version, or it's the exact same version but cleaned up and simplified here, so I'll get rid of this here. Okay, the last thing we got here is RP with respect to B, right? And this vector, I think, was pretty clear. That went all the way back to this original diagram. It's just that green vector here, so you can think of this as just relative position, right, of the point of interest with respect to the body frame here, right? Okay, so again, maybe maybe we should extend this box here, right? Because really, the equation by itself is definitely helpful, but in order to understand it, we really need all of these other bits here, so we understand what all of these terms are. Okay. All right, so there we have it. This is what we were gunning for here, right? This is the giant acceleration term, which describes how the acceleration, the true acceleration, is related to things like the relative acceleration on the body frame and how the body frame is rotating with respect to the inertial reference frame. So everything is baked into this equation. The one thing I want to do here before we take a little break and I'll clear the board here is, in this, there are two very specific and very special terms here. The first is this one I'm going to circle here in red. So this term right here, 2 times the quantity omega b with respect to r cross v p with respect to b here. This term here is sometimes referred to as the Coriolis acceleration. Okay, and we're going to take a look at what that is and how to understand it and look at some examples. The other term that's very interesting is the one let's circle it in blue. It's this thing. It's the omega cross r term here. Oh shoot, and I just looked at this. This is missing a little bar above the r. I really want to make sure this is perfect. Okay, great. So this blue term right here, this is your sometimes also referred to as a centrifugal centrifugal acceleration. Okay, so the Coriolis and the centrifugal acceleration we see only come into play when the body frame is rotating with respect to the inertial reference frame, right? Okay, so with that being said, why don't I take a break? I'll pause the camera, we'll go and erase the board, and I would like to now look at some very interesting examples of how do these terms come into play when you're dealing with a rotating reference frame with respect to an inertial non-rotating reference frame. Okay, so with that being said, let's pause the video. I'll get all this out of the way, and let's get an example or two, or actually like 7 up on the board here so we can really hammer this home and make sure we understand how this works. Okay, so I moved our expression for total acceleration up here to the top left of the board, and let's keep this here for the rest of the discussion here. But now what we want to examine here is a lot of examples of applying this here to a rotating frame. So the first example that I would like to look at is looking at a very common toy that I think everyone is familiar with. It's a merry-go-round, right? So actually what I am going to highly recommend, actually almost say it's required at this point here, is watch this other video here. So what I did here in this video is we went out with a small team here and we filmed a bunch of different examples of the Coriolis effect and the, using a merry-go-round at a children's playground here. So we do all of the examples that we're about to go through right now are all real life scenarios that you're going to see in this video here. So to make sure you understand all those scenarios and so that I don't have to reiterate the setup of that scenario, please pause it right now. Go watch the video. Again, you can get to that video by clicking on the card up there in the top right corner of the screen here. So pause it, go see that, and then come back here. I'll assume that maybe you've done that already. If so, let's go ahead and set this up. So the picture that goes along with this, if you remember here with our merry-go-round, is we wanted to set up a reference frame here. So our reference frame in this case, so FR, let's go ahead and assume this is the Earth frame. And we are going to assume for this case that Earth is not rotating. Or, you know, this is a pretty good assumption because the Earth's rotation rate is going to be negligible compared to the rotation rate of the merry-go-round. So let's pretend we're back there in the 1500s and everybody thought people thought the world wasn't rotating, but it actually was. But let's assume the Earth is not rotating. It is stationary. It's an inertial reference frame here. So that's going to be our reference frame here. And then our body frame here is going to be the merry-go-round here, right? So again, this is our body frame attached to merry-go-round, right? And we showed that in the video here, so I'm just going to go ahead and draw this real quick here. So we are going to have a reference frame here. This is our XR and our YR. I guess we can put hats on these to denote these are the axes here. So this is our reference frame here, right? And I think we said that the observer that's going to be sitting on the reference frame, we called him Randall, right? So I've got a little toy here to denote Randall here. So let's stick Randall on. Okay, and then the more interesting one was the merry-go-round, which was sitting, you know, over here or something like that. Maybe let's draw this nice and big. I want to make sure we have enough room, so I'm not going to run into too many issues here. So let's maybe draw this merry-go-round like that. That's my best approximation of a circle here. And we're going to have an observer here, Brian. He doesn't necessarily need to be aligned here, so maybe let's maybe draw it like this here, right? So this is X body here, and then Y body would be off at a 90-degree angle. Something like this, and here was our FR, or our reference frame here. Or sorry, no, not FR, FB, excuse me, our body frame, right? This is our body frame. And sitting on this body frame was an observer, we called him Brian here. So here's my little Brian diagram, and Brian was just sitting on the middle of that merry-go-round, right? And I think what we said earlier, just to complete this here, we said that, all right, the position vector from the reference frame to the body frame, it's this line, this vector like such. So this is the position vector of the body frame with respect to the reference here, right? Okay. All right, so I think that was what we've got here to set this up. Okay, so let's look at a couple of scenarios in this context and see what happens if we have like a ball. So I've got a little diagram here of a ball that Brian has, and he's going to throw it, and we're going to see how does Brian perceive the acceleration of this ball versus how does Randall perceive this, right? This is what we looked at in the previous video, where we used a drone to kind of look at the overhead viewpoint of this and actually get real life footage and conduct an experiment of this. So let's do a real simple case here, like a case 0 here, right? So the case 0 is, let's just do no rotation. Okay. So in this case, the merry-go-round is not spinning at all. It's just sitting here, right? So, oh, actually, sorry. You know what we should do before we get to our case 0? Let's just make a couple of assumptions that actually are going to apply to case 0, 1, 2, 3, 4, 5, 6, 7, all those. So maybe we better come up with a couple of other assumptions first here, right? So, assumptions. Oh, man, I can't spell this. Assumptions. Okay, so A1, the first assumption we're going to make here is that there's no relative acceleration between the frames. No relative, actually, no relative velocity nor acceleration between frames. Right? I mean, this merry-go-round is not mounted on the bed of a pickup truck, and this isn't driving all around. And Randall, he's not walking around or doing anything like that. The merry-go-round is fixed with respect to this observer, FR, who's just standing there here, right? So mathematically, what's the consequence of this here, right? So this is basically saying that the acceleration of B with respect to R is a big fat 0 vector here, right? That term right here is a big fat 0. Good, so that's going to go away. What else can we assume here? Let's make assumption A2. A2 is I don't want to call it a stretch here, but I think what we can reasonably assume here is that the merry-go-round spins at constant velocity. Right, so we're going to spin this merry-go-round up to speed and then let it spin there and forget about frictional deceleration or anything like that here. Let's just make the assumption that we're only going to observe situations where the merry-go-round is spinning at a constant velocity. So what's the implication here? So the implication here is omega B with respect to R is constant. Therefore, alpha B with respect to R, right? This was the acceleration of frame B with respect to R. Again, this is a big fat 0. So this term here is a 0, which is lucky for us because that's actually going to knock out this cross product here. So with those two simplifications, this equation here, right, actually simplifies quite a bit here. So maybe we should write that down here, right? So we can write down that our total acceleration here, so total acceleration under A1 and A2, right? This simplifies down to something pretty reasonable. A P with respect to R is just going to be equal to A P with respect to B plus 2 times omega B with respect to R crossed VP with respect to B plus omega B with respect to R cross the quantity omega B with respect to R crossed RP with respect to B. Okay? Okay, so actually, what might be a more handy way is we actually want to isolate this term. This is the relative acceleration term, right? This is the acceleration that Brian is going to see on the body frame here, right? So this is the interesting one here. This is our normal true acceleration. So tell you what, let's isolate this. So you can see it's really pretty simple. It's just move the Coriolis term, right? And remember earlier, this was our Coriolis acceleration. And this here was our centrifugal acceleration. Just move those to the other side here. So tell you what, I'm going to write that up here because we're going to use that in a second here. So maybe let's just write this here with maybe I'll draw it like this here. Under A1 and A2, right? That thing simplifies to this where we want to isolate tell you what, let me see. I'll run out of space here. let's do it like this here. This simplifies to A, P with respect to B is equal to A P with respect to R minus the Coriolis term, right? Minus 2 times omega B with respect to R crossed VP with respect to B here, right? And then minus omega B with respect to R crossed with the quantity omega B with respect to R crossed RP with respect to B. Great. Okay, so tell you what, let's extend our little box here because I want to keep both of these here. So here's our merry-go-round simplification of our total acceleration. So let's start examining this equation here now in various of these contexts here. Okay, so I'll tell you what, let's erase all this. Actually, tell you what, I'll pause the video here, I'll erase some of this, and then let's look at our case 0. Okay. Now we can examine here case 0 where there's no rotation. So if there's no rotation and the merry-go-round is just sitting here, right, then omega B with respect to R is equal to 0 here, right? A big fat 0 vector here. So if you look at our expression here for acceleration for the merry-go-round, all the Coriolis and the centrifugal acceleration terms go away here, right? So all we end up with here is that just AP with respect to B is equal to AP with respect to R. So, in other words, it's saying that the acceleration that Brian sees is the exact same acceleration that Randall sees. So there's no difference here. And in fact, if we want to be explicit, we can ask, what is the acceleration? So if Brian is just sitting here and he throws this ball, right? He throws it with some velocity. Well, the ball is just going to move here, right? It's just gonna fly at a constant planar velocity, and it's gonna obviously fall into the board because what? You got gravity pulling down onto it, right here. So it's just gonna fly in a straight line here, and it's gonna hit the ground here, right? Same thing. That's what Brian's gonna see. That's what Randall's gonna see here, right? So actually, we can explicitly say that. All right, if I want to express this in say like the body frame, right? The acceleration that these guys are going to see here is just going to be 0, 0 minus gravity here, right? Because gravity is acting in the, well, here, yeah, x, y. Yeah, so z body is coming out of the page. Z reference is coming out of the page. It doesn't matter in either frame. And you know what? You can actually say that this is the same thing as AP with respect to B expressed in the reference frame, which is the same thing as AP with respect to R expressed in the reference frame, right? All of them can be numerically written as just 0, 0 minus gravity here, right? So that's awesome. We should probably mention here that really, if we're writing this down, what we should be writing down is we're saying that AP with respect to R, right? This is the true acceleration here expressed in the reference frame is going to be 0, 0 minus gravity, right? This is really this is the true acceleration on it, and it just so happens in this case where it's not rotating, the true acceleration is equal to the relative acceleration here, right? Okay, so that's a boring situation. What about something more interesting, like when the thing is actually rotating here? So now let's go ahead and add something. So let's do a case rotation. We'll have some rotation here, and we're going to have Brian throwing from the middle here. So Brian throws from origin of FB. Right, so here's case 1. So case 1 is now this thing is rotating. So frame B has some non-zero omega B with respect to R. So the merry-go-round is spinning here at norm omega B with respect to R. So Brian is spinning around. The body frame is spinning around here, and Randall's just sitting there static here. So we can ask the exact same question here and say, what is the acceleration that Brian witnesses, right? Well, we already solved it for. It's right up here, right? So what do we end up with here? Okay, so again, we've got A P with respect to R, right? That's here, minus 2 times omega B with respect to R crossed V P with respect to B here, right? Minus, and now if you look at this term right down here, right? The one thing that's interesting here is since Brian throws this thing from the origin of FB, let's examine it at time equals 0. The second the ball leaves his hand, if we note here, right? What is RP with respect to B here, right? Actually, and I don't care about expressing it in a vector frame because the answer is the same in any frame here, right? It's a big fat 0 here, right? Because the ball is right there at the center of rotation at time equals 0, okay? So what that means is centrifugal acceleration gets knocked out, right? This 0 is going to, I don't care what omega is here. If I take any vector, cross it with 0, I get a big fat 0. I cross it with something else again, I get a big fat 0. So in this case, the only thing that comes into play here is the Coriolis acceleration here, right? So this is what we end up with here, right? So this is the acceleration that Brian experiences. So again, I think it might be handy here to now express this in a given frame here. So let's go ahead and express this in FB here. So in other words, I'm going to superscript all of this with a B. Superscript, 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 right? Okay, so we got to ask ourselves, what are all of these terms here, right? So again, let's go ahead and recall, right? AP with respect to R expressed in the body frame, right? That is the normal, the true acceleration expressed in the body frame. Well, there's nothing acting on the ball. Let's neglect air resistance and all those other things that might affect it. There's no rocket motor, attached to the ball, right? The second it leaves its hand, it's just a free-falling projectile here. So the only thing acting on it is the gravitational pull down here, right? So this guy is, a bit 0, 0 minus gravity transposed here, right? If we're keeping everything column vectors, right? Okay, here, omega b with respect to r. Omega b with respect to r, all right? This is the velocity vector of this merry-go-round here. So if this thing is spinning around, we see that the velocity vector is actually pointing straight out. So I kind of drew it like this counterclockwise circle, but really the vector is coming out of the page. So it's coming out in a positive direction here. So really what we can say here is this thing, it's going to have a 0, 0, and then the third entry here, sorry, expressed in the body frame, right, is how fast this thing is rotating. In our example here, I want to use an example of, let's assume that this thing makes a full revolution, 2 pi, in 6 seconds. So I think if you go ahead and watch those videos here when we were spinning the merry-go-round, this is a reasonable angular velocity of the merry-go-round. Maybe let's put a transpose in here. Maybe we should put units on this here, right? This is rads per second, right? And this is meters per second squared, right? This would really be, 9.81 or something like that, depending on where you are. Okay, great. So now, what else? Okay, so we got this term, we got this term. Okay, we need this term. We need VP with respect to B, expressed in the body frame here, right? So what we should maybe do is, let me draw that here as another vector here. What color did I use to be consistent with my notes? Okay, purple here. Okay, so let's say that this ball that Brian is going to throw here, here's the velocity vector. It's this purple line here, right? Here is, I'll put the label on it here, VP with respect to B. So he throws it, let's assume Brian just chucks it directly in his x-axis here, right? And let's say he throws it at 5 meters per second. Let's just make up a number here that seems somewhere in the ballpark of reasonableness here for a gentle toss here. So this would be something like 500 transpose, right? And again, this is now in units of meters per second here, right? Okay, so great. It looks like we have reasonable numerical values to put into here. So all we got to do is take these 3 vectors, jam it into here, run over to Mathematica or whatever you like to do this cross product and all of this here. And what do we end up with here? So what you end up with here is that AP with respect to B, expressed in the body frame here, is going to look something like here's the G term, here's gravity, right? So you're going to have 0, 0, basically minus 9.81, right? Meters per second. And then the Coriolis term here, this actually comes out to be something very much not 0 here. You get 0 minus 10.470, right? So look at this. This is actually kind of crazy. If you think about this, what this is saying here is maybe what we should do is we should try to draw this vector here on our diagram here, right? So I've got another diagram here that we can use. And I tell you what, let me prop this guy up here. Got another vector here. So this vector, this orange vector, is going to be the AP with respect to B expressed in B here. So we see that it's got no component in the x-axis here, right? So it's got to be something like this, but it has a 10.4 in the y. So it's like this, right? So it's kind of pointing. I guess it should technically be kind of like that. Sorry, this diagram is a little bit. Let me move this so we can clear this up a little bit, just so we don't have like a million things overlapping. Let me redraw a couple of these things here. Okay, so I gotta write this again. This was frame FB, and it's rotating like this, omega b with respect to r. Okay. All right, so sorry, back to the discussion at hand. It's like this, right? It's exactly lined up with the y-axis here. So this here is a p with respect to b. And I guess it should also be, into the page here, right? Because gravity is pulling this thing down. So this is actually really fascinating here, because what this is telling you here is that the second the ball leaves Brian's hand, normally Randall is going to see this thing just falling down here, right? It's going to go forward, and it's going to arc down and hit the ground. It's going to look totally normal to Randall. But to Brian, he lets it go. Sure, he sees it arcing down due to gravity, right? The 9.81. But there is this weird acceleration here which deflects it, it looks like, to the right. And its magnitude, it's actually even worse than gravity here, right? So this gentle spin of the merry-go-round induces this perception here to Brian, or to an observer in FB, that there is this force that is pushing it to the right here. So, right, we talked about how this is like the Star Wars joke, because sometimes these are called or referred to as fictitious forces here, right? It's not an actual, it's not gravity, it's not a rocket engine pushing it, it's not an electromagnetic force that's attracting it. It's this fact of this perception of a rotating reference frame is where this acceleration comes from here. So it's kind of interesting. The second it leaves, it's going to appear to Brian that this thing gets whipped off to the right here. Right? Okay, that's pretty interesting. So that's case one here. Okay, so let's go ahead, clean up the board here, and look at another example here. Right? So let me erase all this here, because now we're really cooking. This is really getting interesting now. So let's go with, how about a case 2 here. So case 2, again, some rotation, but now if you remember from our video here, let's go ahead and have an observer on the edge of the merry-go-round throw this. So that was, I think we called him Edward, right? E for Edward and E for edge. So Edward throws, let's do this we'll say outward. Okay, so again, let's take off some of these things. We'll put them back in a second once we actually identify where each of them go here. Okay, so we don't need this guy here. I got to get this velocity term off. Okay, so Brian's still, he's hanging out here, and actually the ball, I need to move the ball, because Brian is not throwing the ball anymore. Instead, we got our other friend. Where did I put him? Aha, here, Edward. Okay, and Edward is standing at the edge of the merry-go-round, right on the tip of this merry-go-round here. Okay, and he's going to take the ball here, and he's going to throw it outward. So I'll tell you what, let's move the ball. So ball comes here, and Edward's going to throw this thing. So here is velocity VP with respect to B. Okay, so here's our situation. Okay, so in this case here, now what do we got? Now we've got this green. Let me draw it in green here. So now we can see, and I guess, sorry, it's kind of hard with all these things stacked up here, but I should draw it like something like this. Technically, this green arrow should be exactly on this line here, but that's going to make a mishmash of color. So let's just draw it like this. This is RP with respect to B here, right? It's the position vector of the ball with respect to the body frame origin here, right? It's this green vector. So we see now it's non-trivial, it's non-zero. Here's the term right here in our equation here, so we're going to have to deal with it now. Okay, so in this case, we see the only difference in this is, let's again assume that Edward throws it at the same speed as Brian did in the previous example. So I think, again, we can now say that, the same thing we had was a VP with respect to B is expressed in the body frame. Let's just call it, again, he throws it exactly in the x-axis, so you get 5, 0, 0 transpose, right? And now we see that RP with respect to B, this is expressed in the body frame. This is not 0 any longer here. So I think I measured this merry-go-round. The diameter of this sucker here is something like, I think it was like, let me look. I don't want to guess here. I want to make sure I'm consistent with the notes. What did I say this thing was? Oh, it was 3 meters. Was the diameter here. Okay, so this position vector, the easiest way to describe this green vector here in the body frame here is what? It's 3/2, 0, 0. Right? Okay, great. So all we got to do is plug in all of our numbers up here and then see what we end up with here. So actually, you know what might be helpful here is again, we see that AP with respect to B, right, expressed on the body frame, this is going to be 0, 0 minus 9.81 due to gravity right here. So the only thing that are interesting is again, we see Coriolis here is actually the exact same thing we calculated earlier here, right? So this term here of minus 2 times omega B with respect to R expressed in the body frame cross VP with respect to B expressed in the body frame. This is the same thing we just computed here, right? So this is going to be, what? It's going to be 0 minus 10.470, right? So here's our Coriolis acceleration. Coriolis acceleration. Okay, and now though, this other term, our centrifugal acceleration, right? The omega B with respect to R expressed in the body crossed with the quantity omega B with respect to R in the body crossed with RP with respect to B, which was this thing right here. So you got to take this as just 3/2, 0, 0. Right? And again, for this, I think you plug in whatever it was. We said one revolution every 6 seconds or something like that. You crunch all of these numbers here. What do we end up with? We end up with this is going to be 1.6400. So this is pretty darn interesting here. So what's kind of cool here? I should clean this up so we can actually read this. 6.4. So we see that, okay, what are all of the terms in the expression? Okay, so we got this term, which is right here. So gravity is definitely non-trivial. It's still going to pull the ball down. The ball is still going to hit the ground according to Brian, right? To the guy sitting on the body frame, he's still going to see the thing hit the ground pretty quickly here. But again, he sees this thing whipped off to the right here. So because this thing is minus 10.47. So he's going to see the ball kind of go like that in the negative y direction. But due to centrifugal acceleration, right, he also is going to see it's going to tilt 1.64 so it's actually a little bit like this. I'll exaggerate it here. Right? So the vector, it's not just in the y-axis, it's got a little bit in the x-axis. So this is actually really fascinating. So not only is he going to see it deflect to the right, it almost looks to Brian here that the ball is accelerating away. It's like, yeah, there are rocket engines on the back of this ball that are accelerating it outward in the radial direction here, right? So that's fascinating here, right? And what's actually the other maybe interesting thing to think about here, right, is in the video here, we had Edward on the edge of the merry-go-round. So he was going around and around and around and around here, right? If you think about this, what if Edward was just a little bit off? Like the radius of Edward was, a half, a couple inches more. So he was standing off the merry-go-round, right? So Edward wasn't rotating when he made this throw, but Brian was. What's the difference here? There really isn't any if you think about it, right? The only difference in this case here is that this number is just a tiny bit bigger, right? Right? It's just a little bit larger here, right? So all this is the same. So it has nothing to do with Edward being on the merry-go-round moving around. Edward could be sitting here on the flat Earth. Edward could just be like a stationary, like a pitching machine, right? That throws balls. The thing could be sitting here off of the merry-go-round, and the merry-go-round is going around, and then Brian is going to come spinning, and the second Brian is aligned with this, we fire the thing. It's going to appear the same to Brian as if Edward was sitting on the merry-go-round throwing it, right? Both situations would still see this acceleration to the right and away from the observer here, right? Okay, this is really fascinating. So now we're cooking. We can basically go ahead and, oh, whoops. I was like, what the heck is this thing? Sorry, I should have put this up here, right? This green, this orange vector was trying to be the acceleration of the ball with respect to an observer on the body frame here, right? That's what that was supposed to be. Okay, great. So let's do this again. So remember, in this case, ball deflected to the right and accelerated away from Brian here, right? Let's change this thing very slightly. So maybe again, erase everything. Erase, 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 erase. Ah, shoot, maybe I should have kept that. Yeah, let's keep this here. This is because this is going to be the same here. RP with respect to B. Okay, that's the same here. Oh, because what I'm trying to do now is let's look at a case 3. Okay, so case 3 is Edward now throws, instead of outward, let's do it inward. How about? Right? So all that's different now is that instead of chucking the ball radially outward, let's pull these guys, right? Let's just turn Edward around. Come here, Edward. Face him inward in the merry-go-round. And he's going to now take the ball and throw inward, like right at Brian's face. He's going to throw inward. Okay? So that is the velocity of the ball, P with respect to B. Okay? So the only thing that changes here, right, is this term, right? So now instead of a positive 5, it's like a minus 5 here, right? Because he's now throwing it in the negative x direction here, right? So you go and run this and you see the exact same thing, right? The gravity is here. So really the only thing that changes here is it's this term, right? It's the Coriolis effect is the only thing that's different here, right? So now the only change here is this minus 2 omega b with respect to r cross v p with respect to b, right? All this expressed in the body frame, right? Just plug in all of these things here, right? And what you end up with is this is just going to be a 0, positive 10.47 and a 0, right? So Coriolis is the same here. It has a flipped sign here. Centrifugal acceleration is going to be the same here, right? So I think that's going to be, what do we have last time here? Yeah, this was 1.644 and then a 0 and a 0. It's going to be the same because nothing here has changed. Radius is the same. The velocity, angular velocity vector is the same here. So the total sum of it is going to be Coriolis plus centrifugal and I guess plus gravity here. But since we're talking planar stuff, I can't really draw the gravity thing. So I think it's safe to sort of kind of neglect this gravity thing here as long as we remember that the ball's still going to fall down towards the ground. I'm mostly interested in the planar behavior of the ball here. Okay, so let's take a look at this again. So Coriolis. So we got to draw this total, this orange vector again here, right, is the sum of all these 3 terms here. So, okay, we got this thing. Coriolis is 10.4 units in the positive y direction, which is this way. So it's going to be like that, right? And then centrifugal says that there's some component in the positive 1.64 direction, and so in the positive x, so it's going to be tilted a little bit that way, right? So here we go. So again, in this case, the math backs up what we observed in the video here, right? So again, even though Brian throws it in, it still looks like the ball is going to be accelerated to the right here. The trajectory is going to be bent to the right. And actually, what's interesting in this case is it almost looks like there's like this imaginary sort of retro rocket or something like that, right? Brian is going to see the ball coming at his face at some velocity along the XB axis, but it's actually slowing down here, right? Because there's this component here which is going to kind of appear to him like it's almost pushing back to it. So it's almost like he's got this like telekinetic power that's trying to stop it from hitting him in the face, right? Does that make sense? Okay, great. Now, I think you get the pattern now here. I think what we want to do here is go ahead and start playing with a couple of these here. Let's keep playing with this. So let's go to a case 4, right? So a case 4 is same rotation. Edward now throws, instead of throwing inward here, let's throw tangentially in direction of travel. Okay, so what the picture looks like here is, let's take apart some of these things here, is now This thing is rotating around. So all we're going to do is turn Edward 90 degrees to his right, like this, right? He's going to take this ball, and he's going to chuck it tangentially here. So it's only got a component in the y body direction here. So that's the velocity of the ball here. Okay, so again, centrifugal acceleration doesn't change here, but the only thing that changes here is the velocity of the ball here, right? So now there's no component in the x here, right? And the component in the y, there's all in the y. So this is a positive 5, right? So again, rerun all these numbers. Coriolis is the only thing that changes here. So this Coriolis acceleration turns out to be now, yeah, here we go. So the 10.47 just moves up a unit. So we get 10.470, right? Okay, so then this is interesting. So it looks like they align perfectly in this case. So the total acceleration here, or sorry, the relative acceleration here is like this, right? And it's perfectly aligned with the x-axis here. And again, tilted down into the page due to the gravity term, which I'm not talking about here because this picture is only a planar picture here. So here's my acceleration that Brian is going to perceive here. So at this point, yeah, he's going to, Edward is going to chuck it tangentially. And again, look at this. It appears the ball is going to go this way, but to Brian, it's also going to appear to the trajectory is accelerated to its right again. So again, in all of these situations, it appears that the trajectory gets bent to the right effectively. So yeah, that's fascinating. Let's do the last kind of epsilon variation on this theme here, and then we'll look at something else. So case 5. All right, where's case 5? Where's case 5? All right. Okay, some rotation, and Edward throws tangentially in opposite direction of travel here, right? So again, we're just gonna, let's draw the picture or rearrange our little actors here, our little pieces here. So now turn Edward around so he's facing kind of away, and then to have him chuck the ball that way, right? So we see that, okay, to describe that scene mathematically, all I got to do is put a negative sign here. Okay, and great, everything else stays the same here. So we run all these numbers, and again, all you can do here is you put a minus sign here, and yep, okay. So now look at these two. These two work together, I mean, kind of against each other here, right? The Coriolis acceleration is again the opposite direction of the centrifugal acceleration. So it's still the Coriolis dominates in this case. So really, I should cut off some of this vector here to make this a little bit cleaner, but I don't think I want to do that. So the majority of this here is that it's still in the negative direction here. So this is still going to be bent like this, right? So here's my acceleration of p with respect to b here. So again, same situation. The trajectory is going to appear to be bent to the right here, right? According to this orange arrow here. So fascinating here. Let's keep going here. Let's look at one last case here with this merry-go-round. Okay, case 6. So if you watched our demo here with the drones, remember we told you to remember there was one little weird, interesting case where it would be interesting to look at here. And that was the case where you've got the rotation here and Brian throws straight up. Okay, so Edward, see ya, you're done here. We don't need you anymore. Don't need Edward. Let's get rid of Edward here. Okay. And Brian here as the boy. I guess we don't need this vector anymore. RP with respect to, well, actually, no, sorry. Tell you what, we will need that, but it's not going to be drawn here in the plane here, right? Because Brian is just going to have this thing. All he's doing is throwing it straight up, like straight out of the plane here, right? So let's mathematically describe what's going on here. So, let's erase all these here. Erase. erase, and we'll fill all these in. And I guess, geez, I really probably should have done this earlier and written down our centrifugal acceleration term, but it's just right here. It's this minus. So this is minus omega b with respect to r crossed with omega b with respect to r crossed with rp with respect to b. All of this is expressed in the body frame. That's kind of what we're interested here, okay? Okay, so in this scenario here, right, what do we have? If he's only throwing it in this way, you've got 0, 0, and then I don't know what the velocity of this thing is. At any given time, maybe it's 5 meters per second initially, but let's just call it some velocity. But hopefully, let's postulate that I think there will only be velocity in the z direction here if you throw it in this case. Similarly, if you come here, you get 0, 0, and the ball could be at any height here, right? So this position vector, rp with respect to b, the ball, he's going to throw it, right? And let me see if I can kind of simulate this, right? The ball is going to come up, and then hopefully gravity is going to pull it back down. And I guess like the angle of the camera is going to make this look weird here, but I think you get what I'm saying, right? Oh gosh, I can't do it. But the ball, he throws it up and he throws it down. Watch the video that we had the demo here, right? So what's interesting here is if you look at this here, and maybe what is worth writing down here is, again, omega b with respect to r expressed in the body frame, the the velocity vector, right? We said this was 0, 0, and some number, 2 pi over 6, I think, right? So look at this here. This is interesting here. 2 times omega b with respect to r cross v, this term, right? What is this? Omega b with respect to r, it's something that's aligned and has only a component in the z-axis, right? Crossed with another vector, which, again, I don't know what the velocity is, but I know that it only has a velocity in the z-axis, right? So you got two vectors which are perfectly aligned with each other. You take their cross product, and it's a big fat 0, right? Let's come down to the centrifugal term. Where's omega b with respect to r pointing? It's pointing straight out of the page. Where's the position vector of the ball? It's also pointing straight out of the page. So this term is a big fat 0. So you take this, I don't care how fast the merry-go-round is spinning, you cross it with a big fat 0, you get another big fat 0. So this is interesting. Even though the merry-go is spinning, I don't care how fast, right? This could be going around 10,000 RPM here, right? If Brian, if he's still alive and throwing something from the exact center exactly straight up, right? We see that what happens, the acceleration that he perceives, it's just gravity here, right? There's no Coriolis and there's no centrifugal acceleration perceived for this one special simple case here, right? Okay, so I think this is really cool. Hopefully, we've now got a good mathematical description of all of those scenarios we were looking at here in the other video. So now, let's go ahead and pause the video, and we're going to come back, and I want to look at some other cases of maybe things operating on Earth, something that might not be as contrived as a merry-go-round. Okay, so now let's look at an example using our own planet. So let's look at a rotating Earth. Okay, so let me try to sketch Earth here. So Earth, let's assume it's a perfect sphere for this model here. And you got the Earth here, and then maybe let's draw the equator in red here. And I'll draw a dashed line showing you, it comes around the back of this perfect ball here. Okay, and what else is some features on Earth? Maybe, how about let's draw the, maybe let's label this. Red here is sort of the equator. Let's draw maybe like the prime meridian here. So coming up from the North Pole, going down, it's going to intersect the equator at some right angle like this here. So the blue line is supposed to be the prime meridian, so you're 0 degrees. So maybe let's label this here as prime meridian. Right? And let's make this up here the North Pole here. So this is, let's just label this, how about as Santa? Right? Santa lives up there. Okay? So within this Earth, obviously, we're now smart enough that we realize that the Earth is spinning and going around the sun here. So let's choose two coordinate frames here. So the first one here is, let's choose maybe the body frame. This is going to be the easy one to choose here. So for the body frame, let's go ahead and use what's called the ECEF frame, or the Earth-centered, Earth-fixed frame, okay? So the way that works here is down here in the center of the Earth, right? The core here, where Jules Verne was trying to get to here, right? This is the center of the Earth here. The x-axis comes out and pierces the equator at the prime meridian. So it this and goes right through here, through this point here. This is our x-hat body, okay? The z-axis of this frame actually goes up through the North Pole. So here's my z-hat body. And the y-axis is whatever it needs to be in order to create a right-handed coordinate system with this thing. So I think it's got to do something similar, something like this, right? Here's our y-hat body, okay? So that's our body frame. So this, you can kind of see why it's called centered Earth fixed here, because what's going to happen here is as Earth spins around, this coordinate frame stays with it, right? Because the x-axis always goes through the, I think this is some location in the Atlantic Ocean, I can't actually remember here, where 0 degrees longitude and 0 degrees latitude are here. Okay, so that's the body frame. Let's compare that with what we're going to call our reference frame, or the assumed inertial frame. Let's use this as the ECI here, or the Earth-centered inertial frame. Okay, so the way that looks like is the origin is the exact same. It's here at the center of the Earth here, but the x-axis actually points to some distant star. Maybe let's do this in another color, in green here. So it does, the x-axis comes out and it stays in the plane of the equator, right? So here's my x-hat r, and this points towards a distant star. Distant star. The z-axis is the same as the body frame here, so it comes out through the North Pole here. So here's z-hat r, same. And then again, the y-hat is some system which is going to make a right-handed coordinate system with this. So again, it's going to come out through the equator here, and here's my y-hat r here. So again, this points towards some distant star. So as we go spinning through space around the sun, we've got these two coordinate frames set up, and maybe to help visualize that, I've got a little diagram or a little small prop here. Let me see if we can pull this thing down. Okay, here, let's pretend this is the sun. Pay no attention to the fact that it happens to look like a beach ball and is multicolored. Let's pretend this is the sun. Maybe here, I'll put the orange and red, orange and yellow and red side facing you, so it kind of looks like sun-ish, right? So here is a coordinate frame here. Let's use red, green, blue, RGB for X, Y, Z, right? So red, green, blue, yeah, X, Y, Z. Okay, so let's look at these two frames, the ECEF and the ECI. So this is Earth here, right? Now, the ECEF, I think, is the easiest thing to think about here, right? As we go spinning around the sun here, right? Obviously, this thing makes a revolution once every day here, right? Once approximately every 24 hours, this thing spins around here, right? And I got to make sure I get the direction right. Yeah, it should be this direction, I think, here, right? So as Earth goes around the sun, right? It takes this thing spins at a rate of about 1 revolution per day here, and as we go around, it's going to take 360 spins, or 365 spins about, until we get back to this same location, right? So here's the ECEF. So you can clearly see why this is sort of like considered a rotating reference frame, right? Because as we go around the sun, this thing is spinning around and around and around and around, right? Let's contrast that with the ECI here, or the Earth-centered inertial. What that does here is I got the X and the Y axis are pointing towards some distant star, like towards Alpha Centauri or whatever, right? It's pointing that way, and as Earth spins around, this reference frame does not spin. So its trajectory, as we go around the sun, remember, Earth is spinning here. We just saw that it's spinning, but this thing is always pointing towards some sun, or sorry, so towards some star. Right? So this is the ECI. This is how the ECI frame moves. So you can clearly see that there's an angular velocity vector describing the difference between the ECI and the ECEF frames here, right? So these are our two frames of reference that I want to start playing with here, and we're actually going to see that this is effectively like just a more complicated merry-go-round, right? So let me get the sun out of the way and let's examine this here. So again, in this case here, let's look at our complicated expression for acceleration here, right? What are some valid assumptions? Well, we see that the acceleration of b with respect to r, right? What is this? This is 0, right? Because the origin of these two frames are defined to be coincident here, right? Because, so in this case, they're not accelerating away from one or the other. The origin is always the same. So this is a big fat 0, right? How about this? What is the term here, this alpha b with respect to r? If you remember, this was the angular acceleration vector of these two. Again, if you think about this long enough, this better be 0, right? If this is not 0, we are really screwed. This is like, this would not be 0 in some crazy Hollywood drama here where yeah, the Earth is slowing down or its spin is speeding up or something like that, right? It's been 0 pretty much for all eternity, for as long as we've been recording history, right? The spin rate of Earth is constant, so its acceleration is 0 here, right? Now, what are also some of these other terms? How about omega b with respect to r, right? So again, I think we can easily describe this here, and we can express this in any frame we want, either the b or the r, and I think you'll agree with me that these two are numerically the same, expressing them in either one here, right? Yes, right? So the way this thing spins here, right, if you think about this, we saw it spinning around. The east coast gets the sun first here, so I think this should be, there's no component in the x, there's no component in the y, and it makes approximately 1 revolution, right, 2 pi in 1 day here, right? So I guess in in seconds, so it's 24 hours times 60 minutes times 60 seconds per minute. Something like that here, right? Would everyone agree that this is, maybe we should say this is approximately, right? So the angular velocity vector is just sticking out. Maybe let's use, I don't know, maybe use this to represent the angular velocity vector here, right? So the angular velocity vector is just out the North Pole, right? That's all this thing is doing. And it's got about this magnitude, right? Okay, so with these simplifications, actually, we come into this exact same scenario here where these were the exact same two assumptions we made with the merry-go-round. So yeah, we were just sitting on a big, giant, complicated, circular or spherical merry-go-round here, right? Okay, perfect. So then this is actually interesting. Maybe what we should do here is let's rewrite this, but maybe solve for AP with respect to r here, right? So we could go ahead and rewrite this thing. So acceleration becomes, again, all I'm going to do is rewrite our equation that we had over there, but solve for AP with respect to r, right? So this is AP with respect to b plus 2 times omega b with respect to r crossed VP with respect to b plus omega b with respect to r crossed with the quantity omega b with respect to r crossed with rp with respect to b. Great. Okay. Now, the reason I wanted to do this here is let's consider maybe just somebody sitting here on Earth here, and maybe I want to understand how does a system or an object move sitting here on Earth here, right? What laws govern how an object moves in space here? Well, if you remember, that's kind of Newton's second law here, right? So Newton, his second law, what did that say here, right? It said that all of the forces, right, the sum of the forces is equal to what? The time rate of change of the linear momentum, right? Now, we got to ask ourselves, time rate of change with respect to what, right? With respect to what frame? Well, Newton's laws are only valid in an inertial frame, right? In a non-rotating frame. So this is with respect to r, right? With respect to FR. Now, if we can, let's look at this term a little bit more. What does M look like? For a lot of cases here, right? If you have, like, say, an electric-powered aircraft or like a flying ball or something like that, right? The mass is not changing. It doesn't change with time here, right? It's constant. So this can pop out here. So usually, for most cases, you could write this thing as something like, you know, basically mv dot r, right? Again, just be a little careful, right? You're never going to get to the moon making this assumption, right? Because you're burning a rocket here where the fuel and the mass of the thing is definitely changing with respect to time. So this is only good for, like, yeah, throwing a baseball or a football or something like that here, right? So what is this v dot r, right? This is how the velocity changes from the respect of a observer on the inertial reference frame. That is this AP with respect to r term here. Right? So this thing is just going to be mass times AP with respect to r. Right? Now what we can do here is let's insert this expression here for the acceleration, you can kind of think of this again, this is the true acceleration or the inertial acceleration here, right? Now, let's do that here, and you might think that we're just making this more complicated, but I ask you to maybe bear with me for just a little bit longer here. Maybe I'll keep all of that here. So left-hand side, it's just all the sum of all of the forces, right? All of the true forces, right? The actual forces acting on the object. This is mass times AP with respect to B, right? Plus 2 times omega B with respect to R cross VP with respect to B plus omega B with respect to R crossed omega B with respect to R crossed RP with respect to B. Right? And let me see. Yeah, maybe let's distribute the mass through each one of these terms just for fun here, right? So this is mass times AP with respect to B here, right? Plus 2 times mass omega B with respect to R cross VP, cross VP with respect to B plus mass times this whole quantity of omega B with respect to R crossed omega B with respect to R crossed RP with respect to B. Yikes. All right, finally we got all of that down here, right? So this is, again, F, and maybe what we can do is let's maybe put like a subscript true here, right? These are the true forces or the real actual physical forces acting on by, like, say, by gravity or by engines or by a spring or something real here, right? Now, this term right here, you might think of, you can think of this sort of, this is sort of like the apparent force, right? Because this is mass times apparent relative acceleration here, right? So this is F apparent. Right, maybe we should put a, sorry, we should have had a vector term on this, right? So this is the forces that an observer on the body frame are going to kind of see its effect here, right? So what we can do is let's solve for this. Let's isolate this term. So basically, I just need to move this and this to the other side. So we could rewrite this thing as basically F apparent, right, is equal to the F true minus 2m omega B with respect to R crossed VP with respect to B, right? Minus m times the quantity omega B with respect to R crossed omega B with respect to R crossed RP with respect to B. Here, right? Great, and let me erase this here because I think we got where we need to be here. So what's really interesting about this expression here in this case, we see that the apparent force that an observer is going to see sitting here on this rotating reference frame, it's the true force. They're going to observe something happening here which is explainable or logical, or it seems to make sense to them here, right? But there are these are what are referred to as, sometimes people might call this the Coriolis force, right? And here's your centrifugal force. And maybe we really better put this word force in quotes here, right? Because we see now it's not an actual force, right? It's what's sometimes referred to as a fictitious force, right? Or maybe like a pseudo force, right? It's not an actual force acting on the object. It's a fact that you're sitting here observing the dynamics of the system from a rotating perspective. So that's exactly what we saw in the video, right? You saw that when we did the demonstration of the Coriolis effect, that to an observer sitting on this giant merry-go-round here, right, they see some mysterious force move the ball in some crazy, weird, unexpected way. Well, these are the crazy, weird, unexpected ways, and here's how to quantify both the magnitude and the direction of these quote-unquote fictitious forces here. Right? So it's really interesting. It's not magical space wizards doing Jedi mind tricks on the object, right? It's the fact that you're observing from a rotating reference frame. But here we're able to actually describe them, right? Okay, so you know what? Let's apply this here. So let's keep this in mind here and all of the stuff that we just discussed here, and let's apply this now to say an example of something sitting here being happening on our giant merry-go-round called Earth here. So let's look at how about an artillery shell. Okay, so we'll use this scenario that we've got set up here, and maybe let's assume here that the shell here is fired here with a speed of velocity of p with respect to b. Its magnitude is I don't know, I just Googled this for like, what is a typical artillery shell? I don't know, 1,600 meters per second. So blinking fast here, right? This is pretty darn fast. What else do we know here? Okay, so let's go ahead and calculate things like the magnitude of the Coriolis, quote-unquote Coriolis force or Coriolis acceleration, and the magnitude of the centrifugal acceleration, right? So let's look at first, how about a Coriolis acceleration? Right? So that was our term 2 times omega b with respect to r crossed with vp with respect to b. Right? So you know what might be actually interesting here is, let's look at like a worst case scenario. Like, let's talk about like the magnitude of this thing here, right? What's the worst case scenario? So just by knowing how a cross product operates here, right, we know that this is basically going to be what? It's going to be 2 times the magnitude of omega b with respect to r times the magnitude of vp with respect to b times sine of theta, where theta was the angle between the two here, right? So we know that in order to maximize this, right? So we want this to be 1 here. So I think that occurs when theta, sine is 1 when theta is pi over 2 here, right? So when omega and vp are 90 degrees to each other, we should get maximal Coriolis effect here, right? Or Coriolis acceleration here. So in order to do this here, I need omega b with respect to r and vp with respect to b to be 90 degrees apart, right? Okay, well, great. Let's go back and look at our example here. Well, there's no way we're going to screw with omega b with respect to r here, right? The Earth is, in order to change that, I got to change the spin axis of Earth, and I think a couple of governments are going to yell at us here. So there's no way we're going to change that. It is always going up through the North Pole. However, you can see that this means we're free to fire or shoot this shell however we like here, right? So in order to maximize that, and maybe we'll use this purple here to represent the velocity here, I got to make sure that the velocity vector of this artillery shell is 90 degrees to the angular velocity vector. So there's a couple ways we can do that actually, right? So one thing is you could camp out on Santa's front yard, right, in the North Pole, and just shoot it like this. So basically planar here, right? So you go in Santa's front yard and you level the cannon and you point it exactly at the horizon and you fire it, quote unquote, horizontally, right? Horizontal to the local geography here at Santa's North Pole. So here's one way you could do this here. So you could fire it horizontally from the North Pole, and that will maximize the Coriolis acceleration. So in this case here, you would get the worst Coriolis acceleration possible here, right? Or at least its magnitude would influence the trajectory in a maximal fashion here, right? The other option you can kind of see is, all I got to do is I just got to make sure this purple vector is always 90 degrees to the yellow vector. So I could also come down here to the equator actually, right? And do this, right? You could come to the equator and fire it like that, which in this case you can kind of see that means you actually got to go to the equator. So you got to go to some sunny tropical country, set your cannon up here, right? But instead of firing it, quote unquote, horizontally at the local horizon, you need to, right, turn the thing 90 degrees until it's vertical and basically do one of those those crazy, you've seen all those crazy redneck videos on YouTube where they take an arrow and they shoot it straight up and they run around like they're chicken with their head cut off, trying to avoid the arrow as it comes straight back down. Well, actually, let's see. I don't think it's going to come straight back down, right, according to Coriolis acceleration, because technically here, if you do that, Coriolis effect has a maximal effect here, right? So if you sat here on the equator in your sunny tropical country, you sat down on your lawn chair on the beach, you took your handgun and shot it straight up, I think you'd actually be fine, right? Theoretically, if nothing else was going wrong, because watch, Coriolis is going to bend this thing in some fashion here, right? So let's examine that a little bit more here. Oh, and I guess obviously you can kind of see that this could change. You know, you could be anywhere in the world as long as you are keeping these two 90 degrees apart. It will be the effect is maximized. And maybe this is a quick place to jump in. I think we mentioned this earlier here, but you'll hear people say that the Coriolis effect is maximized at the North Pole and goes to 0 at the equator. I don't know if I totally agree with that statement here, but I understand where they get this sort of, I don't know if I want to call it an urban, this handy little catchphrase, but you think about this, right? So the Coriolis effect, I think what they're mostly talking about is like from a meteorological standpoint, where we talked about earlier, you have these air molecules that come in and go out from a low pressure zone here. So you can probably much see that the majority of that motion is planar to the local surface here, right? So if you were up here at the North Pole here, right, most of the velocity of these molecules here are moving planar to the Earth's surface. Am I describing that correctly? Yeah. Parallel to the local Earth surface here at the North Pole. So yes, if the action is kind of the motion here, the velocity of all these particles are in the purple direction, then yes, I would agree with here that in this case the Coriolis acceleration is maximized here, right? And now as you move down here, as long as the motion of the air molecules stays parallel to the local surface of Earth here, then yes, you can kind of see why, right? As you kind of get closer and closer to the equator, the local horizontal eventually becomes parallel with the angular velocity vector. So now this cross product goes to 0 here, right? So now you would have no quote unquote Coriolis acceleration. But that doesn't change the fact that if the motion or the velocity of the object down here at the equator is like this, you can still have a boatload of Coriolis acceleration here, right? So again, take that statement you might hear about people saying, oh yeah, Coriolis acceleration is maximized at the North Pole and you don't have any of it at the equator. That's BS, right? There is Coriolis acceleration at the equator. You just got to be careful about what direction is the velocity vector here at the equator here. So, all right, sorry, enough gabbing here. Let's go back to this here. So we saw that. Let's maybe consider the case here. How about let's consider this scenario actually that's sitting right here. So consider at equator and shoot straight up. And again, let me put up in quotes here because we kind of see up. What the heck do you mean up? Do you mean towards the North Pole here? No, what I mean by up here is like is locally vertical. Right, so again, that's just sitting there here and pointing your gun straight up in the air and yeehaw, I'm just going to shoot it straight up and see what happens here, right? So in that case here, right, we see that the angle between these things are 90, so this term here goes to 1 here, right? So we see the magnitude of the Coriolis acceleration is this, right? It's magnitude of omega b with respect to r times magnitude of this. Well, what was magnitude of omega b with respect to r? This is basically what? It's 2 pi over 24 times 60 times 60 here, right? What the heck was that number here? I think this is something like, you plug this thing in, you get 7.3 e to the minus 5, something like that. What was this thing? We're firing this ridiculous, this artillery shell, so this here is 1600. Right? So just jam in all of those numbers here, and what you end up with here is the magnitude of the Coriolis acceleration here is, and obviously don't forget the 2 here, right? So this thing is about 0.23 meters per second squared. So actually, this is interesting. This is non-trivial here, right? If you divide this by gravity, like, you know, a reasonable approximation of gravity, meters per second squared here, this is something like 0.023. So, or 2.3% of local gravity. So Coriolis it's non-trivial, right? If you're not accounting for this here, it's you know, it's again, this might not seem like much, only 2.3% of gravity, but that's significant here, right? I think if you run some really simple numbers here, oh, and actually, sorry, maybe what we can do here is let's do one other thing. This is all just looking at magnitudes, right? We didn't actually look at the direction here. But actually, you know, in this case, you can work out the direction of this really simply here, right? Because this cross product is pretty easy. Let's draw another picture here that might help us a little more. This picture is a little bit complicated. Let me see if I can do this. Let me get rid of this. I think we know what our body and our reference frame are in this scenario. So let me get rid of these two here. Okay, and let's draw a top-down view of the Earth here, right? So this is going to be top-down. So the maybe I should have drawn this in red because this is the equator. Yeah, let me do this, right? So the red here is the equator, right? So here's the equator, right? And we're looking at a top-down view of the world here. So again, I guess I can draw. Let's draw some countries here so you can kind of see what's going on here. So the United States looks something like. Here's Washington where I live here, and then you got Texas and Florida. Oh my gosh, I'm a horrible artist. This is supposed to be the US. Oh boy, that doesn't look very good. And then, okay, let me try to draw Europe. What the heck does Europe look like? There's like Spain and Portugal, and like Italy looks like some kind of boot or, oh man, that's even worse. Crap. Europe, right? Here's the Atlantic Ocean here in the middle. So the angular velocity vector here is coming out of the page here, right? So here's omega b with respect to r coming out of the page, right? Okay, so we're sitting here on the equator right here firing our artillery shell, and we're firing it this direction, right? So here, maybe let me grab the purple thing, right? So the purple thing, it's like this, right? This is velocity of p with respect to r. Right? So the Earth is spinning around, you know, in this direction, right? So I think we've got everything we need, right? So we got omega b with respect to r, we've got vp with respect to b. So in order to figure out the direction, I got to take the cross product. So it's omega that way and v this way here. So this term, oh, actually, and sorry, we got to be really careful here. There should be a minus sign in front of this, right? Because there's a minus sign here. So really what you really want to compute here is maybe we shouldn't have skipped steps and tried to bend so much of a shooting from the hip perspective here, right? What we should have computed here is, again, instead of looking at magnitudes, I want direction, so we got to be careful about the direction here. Let me erase some of this. All right. This is basically exactly the merry-go-round, right? This is a merry-go-round, right? It just looks like a top-down view of a merry-go-round. In fact, since we're sitting here on the edge and shooting it in this direction, this almost is exactly the merry-go-round case that we looked at earlier, right? So what we need to be computing here is I want to compute the term -2 times omega b with respect to r crossed v p with respect to b here, right? Okay, so in this case, I think we got -2 times, what's this vector here? So the first vector here, maybe I should have written this as like a square bracket, omega b with respect to r, right? I think let's express everything in the body frame. So this is 0, 0, 1600, right? Yeah, let's maybe assume, that we're sitting here on the prime meridian here. So this is the prime meridian. Actually, we should have drawn it in the same color here. So let's draw it in the same color, blue, right? So blue, this is our prime meridian right here. So you're sitting here in this weird spot in the Atlantic Ocean. So the x-axis of the body frame is exactly in this direction here, right? So here's x hat body, right? So actually, no, sorry, I totally screwed this up. Omega b with respect to r, this is this term, right? It's 2 pi over 24 times 60 times 60, right? That's omega b with respect to r. That's how we describe it. Crossed with the velocity p with respect to b. That is going to be, let me see, we got yeah, 1600. There's only an x component, a 0 and a 0, right? Okay, so you work this thing out here, and what you end up with is 0, negative 0.23, and 0 here, right? So here's your term that is about 2.3% of gravity here, right? So let's just draw this vector here. So you can see here that in this case, this vector here is like this, right? So this purple, or sorry, the orange yellowish one, this here is basically your Coriolis acceleration. Which again, we see here that what this appears to look like here is that the shot is going to be deflected to the right, right? Its trajectory is going to be bent to the right here a little bit. Great. And I think I did some super rough calculations of this scenario here and made some really gross assumptions here about like no air resistance or things like that. But I mean, I think if you run these numbers, like at this point, you could think of it here as almost like, let's draw the picture here from a side view. So again, this is like, you know, there's some palm trees. No, actually, I guess there's no palm trees because we said earlier, you're sitting here in the Atlantic Ocean here, right? So there's a bunch of waves. You're sitting here on some boat here, and it's super hot because you're sitting here on the equator, and you got your cannon, which you have just gone ahead and set up, and you're firing it straight up here, right? Here's VP with respect to B here, right? You're going to shoot this thing up. Well, at this point, you could almost look at this as a very simple trajectory problem, right? The ball leaves the cannon at 1600 meters a second. How long does it take to fall here? Well, you look at this thing and you can say, all right, well, in this case, we see that you got gravity acting down on this thing here, but there's also this Coriolis acceleration that we need to take into account because this boat is sitting here on this rotating reference frame. And we just showed here that here's the amount and here's the direction. So this thing is actually going to bend this. I don't know which way is locally right here, but let's do it something like this here, right? So here's your Coriolis acceleration, right? So you can kind of see here that, you know what, you don't have to worry here, right? Because Coriolis is going to bend the shot as it comes up. And then actually, now let's think about this, because when it comes back down to Earth, it's going to be bent in the opposite direction. So I don't know, we might have to run a simulation to see what is actually going to happen. I know there's other things going on, like centrifugal acceleration, that we should maybe talk about right now, that are probably going to change the effect of this even more. But yeah, I'm pretty sure you don't have to worry. The shot is definitely not going to look like it goes straight up here, all right? It's going to look like it goes up, and it's going to get deflected to the right, as we kind of see in that picture here, the right of its local trajectory. Okay, awesome. Let's do the same thing for, how about centrifugal acceleration here? So let's do a similar analysis for centrifugal. Centrifugal, right? Okay, so for centrifugal acceleration, right? Now we got to have this. We're looking at the term omega b with respect to r crossed with omega b with respect to r crossed rp with respect to b, right? And again, let's look at just the magnitude. Let's forget about the sign, the SIGN here for now here, and just look at the magnitude here, right? So we know that this has got to be less than or equal to kind of all of them by themselves, right? So this is going to be less than omega b with respect to r times magnitude omega b with respect to r times magnitude rp with respect to b here, right? We'll overbound this situation. So we already showed earlier that this number right here, this is about 7.3-ish e minus 5, right? Times 7.3 e minus 5. Now what's this thing here, right? This is the position vector of rp with respect to b here. Well, you can look at it in this picture. The position vector here, it's this distance from the origin here out to wherever we happen to be sitting when we're looking at the centrifugal acceleration. So we're sitting here on the surface of Earth here, so we can see that this RP with respect to B, that's effectively the radius of the Earth here, right? So in this case, let's use a, maybe we should write this down here. So this is basically radius of Earth, right? So that's a friggin' huge number. It's something like 6378.1 kilometers, right? So, and I guess we got to convert that to meters here, right? So this is 1,000 over 1,000 meters per kilometer. There we go. So you jam in all of these numbers here, right? And we end up with this thing looks something like 0.034 meters per second squared, right? And again, if you want to look at this with respect to how much, to normalize this with respect to how much does it affect relative to gravity here, you get something like 0.03. Oh, no, sorry. 0.0034-ish here. Or this is about 0.34% of gravity. So it's not as significant in this case as the Coriolis acceleration, but it is definitely there. In fact, this is what's really interesting. If you look at this, right, the expression for centrifugal acceleration has nothing to do with velocity here, right? You could just be sitting here and not moving, and you would still experience this centrifugal acceleration here, right? So if you think about this, this is actually kind of interesting here. Let's ask ourselves again a situation of where would you get this scenario? This is the worst case scenario here of centrifugal acceleration is 0.34. Where would this be true? So again, we see that, okay, in order for this to be maximized, I got to maximize this cross product here. So I got to make sure that these two things are 90 degrees from each other. So I need to make sure that the radius is 90 degrees from omega b with respect to r. Let's come back to this picture, and maybe let me move these vectors here for now, and let's see if we can figure this out. Okay, so perfect. Let's do it like this. So in order to maximize this, again, there's no way I'm changing omega b with respect to r, right? The spin axis of Earth is fixed. So I have to choose a position vector which is 90 degrees from the spin axis here. Well, where does that mean? That means you're on the equator here, right? The equator is the only set of points which is 90 degrees from the spin axis of Earth here, right? So that means this has got to be on the equator. That's the worst case scenario here, right? Let's now ask ourselves, if you're on the equator, where is this quantity omega b with respect to r crossed with rp with respect to b? So let's draw it here. Let's maybe look at, it doesn't have to be here on the prime meridian. Let's look at this anywhere here. Let's look at like here. Like say you're sitting here on the equator. So here's my position vector. I guess maybe I'll draw it in blue here, right? So blue is rp with respect to b, right? So let's look at this. Omega is coming out of the page. Oh gosh, I'm gonna run out of fingers. X is omega, right? And then y is going to be rp with respect to b. So that's the blue line. So these fingers are supposed to be blue, right? Oh gosh, I'm really running out of... Basically, what I'm getting at here is this quantity is a vector that's 90 degrees from r, right? So let me do it like this. Maybe let's do this one. So there, something like that, right? So this this yellow orange line, this is going to be the direction of omega b with respect to r crossed rp with respect to b. Would everyone agree? Right? Yeah, let me think about that. Yeah, omega comes out of the board. Yeah, that way. Yeah, I think, oh, here, that's a better angle, right? Omega comes out of the board. My middle finger is in the direction of the position vector, and my thumb now points in the direction of omega crossed r, right? Great. So now let's look at what is this crossed with this quantity again here, right? So I got to now cross my finger coming out of the board, and now we see that I got to turn it like this. So my middle fingers are aligned with the yellow vector here, and now all this does is it turns at 90 degrees again. So now this yellow vector is basically going to be omega b with respect to r crossed with the quantity omega b with respect to r crossed rp with respect to b here, right? So this is interesting. So on the equator, it's the centrifugal acceleration is maximized, and in fact, it points directly back into the well, sorry, we got to be careful. This thing of omega b with respect to r cross omega b with respect to r cross r b with respect to b, that thing points in that direction here, right? But again, we got to be a little bit careful here, because now let's take the sign, the sign of this into account, right? There's a negative sign in this expression in order to get total of the apparent acceleration here of an observer on the body frame here, right? So again, what we should be computing here now is, I want negative, let's do this first one here, right? So I want negative of the entire quantity here. Maybe let's do it like this here, right? So this first vector here is 0, 0, 2 pi over 24 times 60 times 60, right? That crossed with, same thing, 0, 0, 2 pi, 24 times 60 times 60, right? Crossed with this position vector here, and I guess in my notes here I use something, again, very, very simple here. I think I used the example, where did I define r? Come on, where is it? Well, again, I think I used the example of sitting here on the prime meridian here just to be able to express this position vector in a convenient fashion. It shouldn't really matter where you're sitting here, as long as it's sitting there on the equator. Why did I not write this thing down here? Where did I define r? Oh, here it is. Yep. So this is going to be that huge number. Right, so the radius is this giant thing, right? 6378.1 times 1,000 meters, and then a 0 and a 0. Right, and then I guess I got to close this bracket over here. Great. So if you run all these numbers, this whole thing comes out to be something like 0.0340 here, and again, this is units of meters per second squared here, right? So again, the scenario that we're looking at, crud, we're running out of space here. What do I want to do here? Yeah, let me clean this up just so we can very cleanly express what we're doing over there. So let me get rid of this blue line. Maybe I should have just kept this thing simple. Right? So we're looking at a scenario of the artillery shell or like a human body or someone sitting here at the equator, the intersection of the equator and the prime meridian, sitting there in the middle of the Atlantic Ocean here, and all they're doing is just sitting here, right? So this term of centrifugal acceleration here it looks like that. It's positive 0.34, so it looks like this. Right? So the positive, so it's in this direction here, right? So you got this. You got, this is centrifugal acceleration. Right? So now what's interesting again about this here is let's think about what other forces. Well, we saw here that in this case, if you're just sitting here doing nothing, there's no Coriolis, right? If you're just sitting here in your lounge chair, the velocity here is 0, so there's no Coriolis. So the only apparent acceleration that you're going to observe on this rotating frame is the true acceleration and then the centrifugal acceleration. Well, what's the true acceleration? What are the forces when you're just sitting there with your butt in a chair on this boat sitting in the Atlantic here? Well, it's just gravity, right? But gravity is working in this direction, right? So here's gravity in that direction. So what's interesting in this case is centrifugal acceleration sort of opposes gravity here, which again, if you think about this from a merry-go-round perspective, this kind of makes sense here, right? Centrifugal acceleration is sort of this center-seeking acceleration here. So as long as you're sitting here on the radius here, you know what? You actually weigh less there. You weigh less on the equator here, right? Because the total acceleration in the downward toward the core of the Earth is going to be 9.81 meters per second minus this 0.034, right? So this, crud, I don't know if I actually wrote down the number here. Did I write the number down? whatever, I'll let you run this number. You can kind of do this math, right? So there's a little bit, you weigh a little bit less on the equator, and actually it's not totally trivial. So for example, like, let me see here. Did I do a little example here? So let me see. So example, let's consider a 70 kilogram person. I think this is something like, you know, around 154.4. So this is like 154.4 pounds mass, right? Again, your mass obviously doesn't change if you're sitting at the North Pole or the equator. However, your weight does here, right? Because of this difference between gravity and centrifugal acceleration. So what ends up happening here is this same person here with the same mass here, when he's sitting there up at Santa's workshop at the North Pole, right? This guy weighs 154.4 pounds force, right? But here at the equator, right, he actually weighs 153.85 pounds force. So here's a pretty simple way to lose weight, right? So forget about Atkins or South Beach or whatever diet you want to do. Just move to the equator and you lose over half a pound instantly here, right? So actually kind of interesting. So, yeah, I think, you know what? This might be a good spot to leave this discussion here about velocity and acceleration here for systems in rotating reference frames. I guess maybe no, I'll tell you what, let's look at one more kind of interesting example related to accelerometer. So I'll tell you what, let me pause the camera here, erase the board, and I'll be right back in a second. Okay, I wanted to talk about one last potential application of this here. Let's take a look at it like, for example, like an accelerometer here, right? So I've got this small 3-axis accelerometer, right? It's just, for those of you who have maybe played with these things, you know that an accelerometer is really just sort of a proof mass inside a casing here, and it's supposed to just measure accelerations here, right? But now what's interesting is, within the context of this discussion, is what acceleration does this thing measure here, right? So if you look at this equation, oh crud. And I just noticed this term is missing a bar. Shoot, I've just been yakking for the past hour and a half missing a bar. So anyway, correct your notes here. Hopefully that's a really minor detail here. It should have had a vector symbol on top of it here, right? But again, let's go back to the question. What is this thing measuring here, right? This thing is going to be mounted on the body of an aircraft. So maybe let's draw this here. Let's draw like a big old Earth here. Right, so again, here's the center of the Earth. Let's maybe make here's my X reference here. Here's my Z, I think, Z reference, right? It was coming out of the North Pole here, right? So here's my Earth, and you've got an airplane, right? Sitting on here, and you mount this accelerometer inside the body of this aircraft here, right? And let's attach a frame to this here, right? So here's maybe your X body frame, and then maybe the Z body like this, right? So again, the question is, what does this thing measure here, right? If you think about this long enough, right, this thing has no idea if it's sitting on a rotating reference frame, or heck, it should have no idea if the Earth is rotating or not. So really what this thing measures here is true acceleration, right? So the accelerometer is going to measure this term, right? So accelerometers measure this, right? However, you can probably imagine, though, if you're navigating on Earth, right, on this reference frame here, or on doing something relative to maybe your body frame here, you might want to be doing things like asking, well, what's the relative acceleration here, right? So we can quickly see here now that you might have to correct measurements by this if you're trying to infer that, right? If you're trying to infer the acceleration of the body with sorry, did I just point to the wrong thing? I think I might have pointed to the wrong thing, right? The acceleration of p with respect to b here, right? Although this term, you might want to start asking yourself questions about, is that 0? You know, we made some of these assumptions that said, you know, this was 0 or this was 0. So in the case of this maneuvering aircraft, right, if you think about this, as this thing flies over Earth, right, maybe later on you're up here, right? XB, ZB. So you can clearly see here that there was some rotation here going on top of maybe any of the other rotation of the aircraft. So you can see that this gets a little bit tricky pretty quickly, but hopefully we now have the framework and the fundamentals down that we can use some of these tools to bring to bear on questions like this here. So yeah, that sounds good here. I think this is probably a good spot to leave this. So I hope you enjoyed this discussion on velocity and acceleration in rotating reference frames, and now see that this motion is not the product of some dark Sith art, but rather it stems from the fact that we live on a big, giant, rotating, non-inertial reference frame. And actually, since we're talking about the Sith, maybe I'll give this a try. You will like, share, and subscribe to my channel. These other videos that YouTube is suggesting are not the videos you're looking for. You want to find more videos related to vector mechanics, control design, and engineering on my channel and click on them. You can then go about your business.